Hi, I'm Feng Liang from Ignition Point in Japan. I'm here on behalf of my co-authors to present the work OmniView, an exploratory study of 360-degree vision using dynamic distortion based on direction of interest. As we all know, the human eye has a good depth perception but limited field of view, which is around 180 degrees. Therefore, it's impossible for us to perceive the world like an animal with molecular vision. But these days, there are ways to augment human vision using devices like 360 camera. However, we wish to emphasize that our research question is not can we adapt to 360 vision? Rather, our research question is what is an appropriate 360 vision for us? As the contributions of our work, we present OmniView, an adaptable solution for optimizing 360 FOV vision, and explore the effects of it on spatial perception, reaction time, and simulator sickness. Furthermore, we discuss design solution for future wide field of view enable devices based on the obtained results. Let me introduce some of the related works. Works related to spatial awareness augmentation, like the haptic color, heat nav, insight. We find them relevant in understanding the effects of augmenting the user with different sensory perception, and also the works related to visual augmentation like fly width, spider vision, unconstrained lag. One of the most related works to ours is the fly width. Since the camera renders the surroundings onto a flat plane in front of the user is provided with an rectangular projection that is able to show the full physical environment around them. These works introduce several methods to view contents beyond the typical FOV, yet only fly width actually allows for constant 360 viewing. And the works related to projection methods, like this one we show here, and also the Rich 360. Most of them use different kinds of projection methods to optimize 360 vision, which are related to OmniView because we use dynamic distortion based on a rectangular projection. Okay, let's move to the implementation part. About the hardware, the prototype consists of a Vive Pro eye embedded with eye trackers and a record theta V 360 camera mounted on a helmet worn by the user. And to run our system, we use Alienware Area 51 placed on the desk, and our system runs at around 20 frames per second. For the software, our system was implemented using Unity 3D game engine. The virtual projection camera is placed in the middle of the 360-degree video from the theta V video feed, and we mathematically convert from the polar coordinate system to the Cartesian coordinate system. In the formula I show here, the obtained value of x, y, and z are coordinates of each pixels present within the QMap. We then add the modifiers x1, y1, and z1 with a value range from -1 to 1 to treat each distortion direction. A positive modifier will enlarge the distortion of one direction, and the negative modifier will enlarge the opposite direction. We build 3 variations of OmniView. Each of these versions mainly differs in the method to activate the distortion. All of them are implemented with 1 second zero base selection, and this is the first one. The first one is the gaze OmniView. It activates the distortion based on user's eye gaze, and the gaze OmniView benefits with hands-free. The second one is pointing OmniView. It uses a VR controller to activate the distortion. User points towards the actual direction to activate the distortion. Pointing OmniView is not hands-free, but it might improve spatial perception because the user has to physically point the controller. The third one is automatic OmniView. When the camera detects a person's face, the distortion will be activated. Automatic OmniView removes the control from the user and is designed to allow automatic distortion for conversation. In order to evaluate the spatial perception and reaction time of the participant using our system compared with the conventional rectangular view, we conduct the user study 1, which is a searching task in virtual environment. During the training phase, the participant can freely move the selection cube, which is constrained to the surface of the semi-transparent sphere. When they move it, it is visible in the planar projection view and moves relatively. Then the target phase begins. The target cube will appear around the user at a fixed distance from them and projected on the planar projection for 10 seconds. When the target cube disappears, the participant is required to place the selection cube in order to indicate where they think the target cube was relative to them within 10 seconds. Then the target cube randomly appears 3 times for 6 positions, so it is 18 times of target and selection for each conditions. We have 16 participants, each undergone all 4 conditions. During the study 1, we record the distance between target cube and selection cube, participants' reaction time, and also ask the participant to answer the SSQ and NASA TLX. As the result of study 1, since the SSQ results showed no statistical significance between the conditions, there was no noticeable increase in nausea, oculomotor problems, or disorientation. And there was also no statistical significance between rectangular projection and OmniView. By analyzing the spatial distance error and reaction time. And there was no statistical significance in TLX, suggesting that each of the implementation did not have any higher perceived task load over another. The highest score on average is the pointing method. Looking at the correlation coefficient between reaction time and spatial distance error across all conditions, there was a strong positive correlation between each of the conditions' reaction time with its spatial distance error. Only the p-value for the equitangular distance was below 0.01, suggesting that the longer it took to react to an object, the bigger the spatial distance error. And this is most prevalent using equitangular. Finally, we look into the correlation between the SSQ score and average perceived task load. Overall, there was a statistical significance positive correlation between the TLX and SSQ for all conditions. The pointing method and automatic method had the highest correlation coefficient, followed by the equitangular and gaze method. Besides of study 1, we conduct study 2 to evaluate the possible effects of OmniView on similar sickness when used in physical space and performing simple everyday tasks. Participants were the same as study 1, each also undergo all 4 conditions, and the apparatus is similar but with the addition of real-time 360-degree video streaming by wearing a helmet with a θV 360 camera mounted on the top. And in study 2, participants were required to wear the prototype and perform 3 activities, which I show on the right side. The first one is the talking while seated for 2 minutes, and then reading a book on a tablet device while seated for 2 minutes, and finally walking to and fro for 2 minutes. Each participant performed these activities back to back without pause. Participants were asked to answer SSQ before and after use of each conditions. According to the SSQ results, there was a statistical significant difference in induced disorientation. And also, there was a statistically significant rise in disorientation from the pre-study to after the use of the automatic and pointing methods. We believe that this is due to how OmniView works, during which a spherical to planar projection is shown to the participants at all the time, and allowing them to actually see all direction projected onto a plane. And since this study is streamed from a 360 camera with limited resolution, which increased the disparity with their actual vision, this could also overall contribute to stronger sickness. In conclusion, we propose an exploratory study on optimizing 360 FOV towards human vision's augmentation. For a fair comparison, and we compare OmniView with equitangular method as baseline. We introduce 3 variation of OmniView. Since the pointing and automatic OmniView induce significant disorientation, we recommend a gaze-based method as the preferred mode for distortion change. Even though we did not find any significant positive effects on OmniView over the conventional rectangular, these exploratory studies provide us with several useful insights on pushing the boundaries of 360 vision augmentation. It is important that we establish that OmniView also had no significant negative impact. For the future works, we will look at long-term studies and evaluation using OmniView. We also plan to integrate OmniView with other spherical to planar projection like the Mercator, Winkle Triple, and anything else, and allowing us to compare with between wider options for OmniView. That's all. Thanks for listening. Hope everybody stays healthy and we can meet somewhere in the future. See you.